The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Can you hear me? I think we may have a problem with the audio. I am checking now with... Yes, okay. So I think you can hear me. Also, I will verify with my colleague if the screen is available. Yes. So welcome today to this webinar about composite floors according to the Eurocode 4. We will be talking about the whole functionality of SCIA Engineer, including the analysis and all modeling and the check and design capabilities. A few words about the webinar itself. So also I'm just going to check that I'm showing the correct screen, and no, of course not. So now you see the correct screen, and so the few things that I would want to say is that during the webinar you can at all times ask questions via the question tab on GoToWebinar. And I will come back to the questions after the main part of the webinar, of the presentation. Also, today I will present it in SCIA Engineer. Let's say we will start with a live session in SCIA Engineer, and then I will answer your questions, and then I will go through a small presentation that I made in PowerPoint just to repeat the important things that we mentioned during the live demo. After the webinar, I am planning to send you these handouts, this presentation, and also I'm working on a tutorial that will be made available. The webinar will be recorded, so you can find it afterwards on our YouTube channel. And also all attendees will be muted during the session. So now I will switch directly to SCIA Engineer. I will get rid of this presentation and I will come back to it afterwards. So today we will convert a standard structure in SCIA Engineer to a composite structure, let's say a structure with composite floors, and we will run the composite checks, and we will also run the composite design, which lets us optimize cross-sections, stats, etc. So I've already prepared the models, so we only have 1 hour, or let's say a little bit more than an hour for the webinar, and because of that I've already done a lot of the work in advance. So I've modeled the structure, and now I will show you more or less what I've done. So here you see already the frame, so all the steel members. What I've done is I've gone to structure, I've used catalog blocks, and here I've used the 3D frame option, which allows me to model a 3D frame, selecting some sections for columns, beams, and beams in the other direction. Then I've added these catalog blocks to the origin of the global coordinate system, and I've also let's say added some irregularity, because I wanted just to show you what happens when you don't have a fully regular structure. I believe that the ones of you who are designing composite floors, you normally have to deal with some geometry that is not 100% regular, and because of that I included this irregularity. After that I added some bracing. Also I will at some point in the webinar run some nonlinear analysis with tension-only elements, just to demonstrate that you can combine this with the current functionality for composite. The next thing to mention is the boundary conditions. So nothing special here. I have, let's say, For the strong axis of the columns, I've added rigid support. In the other directions, it is hinged. And what I've also done is I've added hinges on all of the beams. So here you will see both the primary beams and the secondary beams are hinged. What I've also done is I've added all loads. So let's first show the load cases. To not waste time during this presentation, I've added a bunch of load cases, self-weight, some loads during the construction, permanent loads, live loads, snow loads, wind loads. And if we look at the load service, I will show you what I've done. So self-weight, that's just automatic. I haven't really done anything there. For the other loads, I've used free loads, and this allows me now to before adding my 2D members, to apply the load in advance. Interesting for the ones of you who don't know the free load functionality, but it allows me, for example, to add a load with validity from, for example, 0 meters to 11 meters. So here practically I have 10 meters and a half, I think. So if we look at the node, 10 meters and a half. So this free load will apply an intensity of 1 kilonewton per square meter on all of the composite floors that I will model at these levels. And I've done this for all of these load cases. So you can see for permanent loads, I have one load for the roof with validity from 11 meters and above, and also another load for the floors. Then also the live load I've modeled in the same way. Also taking into account pattern loading in one load case. I've put these two load cases in one load group, which is exclusive, which means that they will not be considered at the same time. And I've done the same for the roofs. These are all SCIA Engineer tricks that let me limit the amount of time that I spend in modeling here. The same for snow load. And wind load, there are some, I try to make it as realistic as possible, adding some line loads on columns as well to more or less simulate 1 kilonewton per meter wind pressure on all surfaces of the building. So that's more or less everything that I've done in advance. And now I will add my composite floors. So what I will do is I will go to 2D members, and under plates there is the item composite deck. So I will select this, and when I select it, what I see is the properties of the 2D member with automatically set defaults. So this means that you can model a composite deck and convert it to anything you like afterwards. So here I define that this is a composite deck via the element type. And here automatically I have the property rigid diaphragm, which means that for the lateral loads, I will have a rigid body to take the load, the lateral load. And for the gravity load, I will be using the method of tributary area, which is set here by default. I will also select profile steel sheeting. So I'll just grab one of these sheets and I add it to the database. Okay. And then here I will select it. You can change the material. In this case, it's not so important. Of course, you can change it to the correct cold form steel material, but this is only taken into account in the composite design for its E modulus, so it doesn't really make a difference what steel grade you select for the sheeting. Then I have here the concrete deck material. Let's switch to 15.5 centimeters deck thickness. And this is everything that I will set up now. So I will now model the composite deck. Here I will go and select all of the nodes. It's let's say better safe than sorry. If you have a more irregular geometry, maybe you can just draw a line from corner to corner, but I would like to be safe today, so I would just select all the nodes. So here I have my composite deck. So I press escape and now it tells me this project contains a composite deck member. partial self-weight load cases for fresh and dry concrete will be automatically generated. In addition, automatic combinations is enabled, so the existing automatic combinations will be replaced by those prescribed for composite. So what you see here is that SCIA Engineer has an automatic handling of a few things when it comes to composite. So on one hand, we have the stages. So you don't have to use any advanced construction stages. What SCIA is doing is it will automatically in the background consider different stiffnesses in different stages. So we have construction stage, final stage, creep also in the final stage in certain cases. And on top of that, your increased weight of concrete will be taken into account in construction stage. So thank you, SCIA. It generated some additional load cases. Let's have a look what is the situation. We go to load cases and we see these two load cases. I will just move them here. We have fresh concrete and we have dry concrete. Okay, I will go back to structure. And then I will just copy this slab everywhere and hide additional data, yes. And like this. So now I have these 2D members. What I will do is for the roof, I will just switch to metal deck. Let's say that on the roof we don't have any concrete. We only have the steel sheeting. Automatically we have flexible diaphragm. You can also change this property here. Also we are using the tributary area method for the distribution of loads. So now when I model these slabs, I see these lines appeared on my 2D slab. And I see these are the tributary areas. Well, in fact, they are not as I expected. I will switch to one floor and I will show you. Now it seems that all of this load will go directly into this primary beam. This was not my intention. And what happened now is if I look at the 2D member, there is this indicator which is showing me the direction of the troughs or the sheeting ribs. And I see that these ribs are now going parallel to the beams, which makes no sense. How should I control this? There is this link. There is a link between the local coordinate system of the 2D slab and the sheeting orientation. So I go and I select this local coordinate system angle and I will switch it to 90 degrees. And so now you see the ribs are parallel to the primary beams, which is what I want. And as a result, the tributary areas changed. So they are now better. Can improve them even more, but let's do this, not forget to do this for all of the slab. So here I will switch to 90 degrees, and so all of the floors are now identical. Switching back to activity, I will select again the slab and we will look at the tributary areas again. We see that here it's still not perfect. If I select this tributary area, I can see that beam 158 is carrying all this load. Why is this happening? If we look at the properties of the 2D member, we see this property called maximum angle for transfer. So this means that if a beam is more than 5 degrees not perpendicular to the load-bearing direction, it will not be considered in the load transfer. Well, in this case, I can adapt this tolerance. We can call this practically a tolerance value. And if I change this value, I see that also the tributary areas are changing. So still not good enough. Okay, so now for an angle of 12 degrees, we see that the tributary areas are looking much better. Let's do this again for all of the slabs. So I will select all of the slabs. And then here, angle 12. And if we look from above, it seems that all of the tributary areas are looking good. I will remove the names of the beams. And now let's turn off these tributary areas. We've verified that they are okay. So here under structure, the first tab in the view parameters, there's tributary areas. You can hide them. And you can activate effective width. So now when I look at my structure, I don't see any effective widths. Why is that? If I select one of the beams, I see that this is simply a beam. In order to use the composite beam design in SCIA, you need to work with plate ribs. If I connect these beams as ribs, then I can use all of the composite functionalities. So now what I would do is I will use this property connect members and nodes. But of course, I don't want to include any bracing. So if I select all of the bracing, I want to remove it. I select all the beams. I go to connect members. And there's the property connect 1D members as ribs. Okay. So intersections have been generated and 152 beams have been connected as ribs. Okay, so now SCIA is thinking, and here is what we get. Don't panic if you see that your effective widths look like this. They are normally recalculated when you run the analysis. If you want to see them immediately, just select one of the beams, and there on the bottom there is calculate effective width. So this will work for that floor level. And so if I run it for this floor, you see that the effective widths are now calculated. Another thing you can do, I like the mesh generation option because it runs many automatic things that happen before the calculation without running calculation. So, for example, if you have, in my case, free loads, it will generate loads, it will generate effective widths, etc. So I think I can use activity again, like this, and we will look at the effective widths. So far, it's looking good. Here there is some overlap. If you would like to overwrite this value, it's still possible. So the effective width is managed from the property of the 1D member, and there you will find shape of rib automatic. If you want to change the values of effective width, you can switch it to manual. So it will preserve the calculated value, but you can still use it as a basis. Sorry, this is for check. So you see two values. One is for internal forces, so for the analysis, and one is for check, which means for the composite check in this case. So you can see immediately the effective width is adapted. I will still use the automatic option, and again, I can press calculate effective width. So these are my effective widths. Another thing that is important to realize about the composite analysis model in SCIA Engineer are a few other properties of the 1D member. So we see this is a plate rib. And here the next property is analysis model. In this case, I will stick to the standard option. The cellular beam option is important if you would like to model composite beams and export them with our Westtalk link. Then you can use this option, cellular beam. Then the next very important option is this type of connection with standard composite action, with advanced composite action, without composite action. So here, because I had a composite slab and I connected beams to it, automatically it sets the default, let's say, correctly. So the standard composite action is converting the model into some sort of a hybrid where on one hand, we place into one level beams and slab. I will show you here. If I go to set view parameters and I show the analysis model, here you will see that on the level of analysis, here is the slab and the beam is in the middle. So why is this? The reason is that if you take into account the eccentricity on the level of the model, you will get normal forces in your composite ribs, which will then cause problems in design, because according to the Eurocode, we are designing for bending moments and shear forces and not for normal forces. So what happens now in SCIA Engineer with standard composite action is it places the beam in the middle, but it also takes into account that this beam has much higher stiffness because of the concrete which is on top of it. So the stiffness is calculated with the concrete and also taking into account partial composite action. So here I've set default value for the composite action is 55%, which means that still beams and slabs can slip between each other. Now, if I set this to advanced composite action, then the beam will go, it will look really nice, like the beam will be underneath the slab. But keep in mind that here you will get very large normal forces, axial forces, and also your bending moments will be much lower. So when you run the composite design according to the Eurocode, you're not going to be in a safe situation. Now, what can we do to show, to still use this analysis model, but show the structure nicely? We will use the structural model. So in the structural model, I've already defined here that my 2D members are aligned at the top. So at the top of the flange, I have my system line, and I can also do this for the 2D members. Where's my 2D member? I will grab it from, it's probably not active. Yeah, it's possible it's not active. So, or maybe I have a filter. Let's just switch to structure. So here I will switch again to the nice coloring, and there is the 2D member. I will select all of the 2D members, and then I will go to structural model. So this, whatever you do here, it doesn't influence your analysis results. And then I will align at the bottom of the 2D members. So as a result, do I see it correctly? Right, I will just extrude once again. Oh yes, okay. So here you can see that the slab is on top of the ribs. Okay, maybe that way it will be more clear. So this is more or less everything related to the modeling. And now I will show you the loads. So here, what is interesting, I edited something in this slab, so I will run mesh generation again so that all the loads are generated. Let's switch to the first load case. Okay, saving loads. Okay. Yeah, okay, it wasn't finished with mesh generation. So I will now switch to the self-weight. And as you know, normally self-weight is hidden in SCIA Engineer, but in the case of composite slabs, you will be able to see the weight of the sheeting. So here you see these composite decks, including the metal deck, has self-weight of this value, which is practically just the sheeting. So this is calculated based on the geometry of the sheeting. Now the fresh concrete is only on the composite slabs. And so here what we do is we calculate the weight per square meter taking into account the sheeting geometry. So those parts that are empty space in the sheeting will not be counted. And so we obtain this value. For dry concrete, the value is slightly less. What is important here is that you can see the different densities in the material library. So if we find here our concrete material, we will see unit mass is 2,500 and the density in fresh state is larger. You can adapt this value if you add it, like if it's larger, then you will also get a larger values in your analysis model. There is a possibility to turn off this functionality altogether via the composite setup, but we will not talk about this now. So here, if I go to my other load cases, I will activate in the loads to see original plus generated. And what I see here, how is this load applied now? I'm using the rigid diaphragm with tributary areas. And so you can see I have a load applied here as free load, and that gets transferred to the slabs, actually to the beams, via the tributary area method. And you can verify this on the structure. So this is the case for the construction load. For the permanent loads, I have some loads applied on the composite floor, also on the metal deck, values with lower intensity. The live load, the pattern loading, you can see it here. If you have value of 3 kilonewtons per square meter, I think the spacing of the beams is 8 meters. And so 8 divided by 3, right? Three spacings times 3 is 8. So very simple to calculate and verify. In the case of the regular geometry, in the case of less regular geometry, you may get some edge effects like this, because you see here the load is trapezoidal or linear, and so more loads will be generated in this case. But for the regular spans, it's very easy to verify. The same for the roof. Also the pattern loading, the snow loading, the wind loading. Here we will look from below, the suction on the beams, and the other wind load case. Now what is important here is in the load case menu, you have this property which is called staged for composite analysis model. And there every load case is set in different stages. So the only thing you need to do in order to run the construction stages correctly for composite is to place your load cases in the correct load stage. And this is also, there is some intelligence to detect. So if you set some loads which are, for example, of type self-weight or load group construction, it automatically gets set to construction stage. Also for the dry concrete. For the other load cases, you have a choice, and normally permanent loads go to final stage long term and variable loads go to final stage short term. What is the difference between the two? In the case of long term, we will also take into account creep deformation in the concrete. So all of these load cases are final stage short term. So I've set them up correctly, and that's everything I need to do for the stages. In addition, I have modeled here some load groups in order to take the relationship between some load cases into account correctly, and combinations are generated automatically. So here you can see there is a little bit of abbreviation going on here. So CS, that's construction stage, ULS, construction stage SLS, final stage ULS, final stage SLS, and this last combination is the accidental. It is used in the fire checks for composites, which I will not show today, but you are of course free to experiment with these yourself. So these are the combinations. If you add more load cases, they will automatically be added to these combinations. Result classes. One result class, which is very useful for composite design, is this one. It gets generated automatically, and it contains the ULS and SLS combinations for composite. You can also create your own class if you would like to. So this was all the modeling, including the loads. And now let's calculate the model. I think I also should have run check structure, but we will see if there are any problems. Another thing which I forgot to mention is that it is advisable to also check your buckling settings when you have a steel structure like this, especially for your primary beams. Sometimes the automatic detection of buckling lengths doesn't work automatically. And so what I've done, even before adding the composite slabs, I have selected all of my composite secondary beams like this, and I've assigned to them the same buckling settings. So here you can see nothing special here. The span is between these two supports. Like here I see all of the beams that share these buckling settings here. And nothing really special for the case of the secondary beams. In the case of the primary beams, it sometimes happens that these are activated by default. So it's important to have your span determined correctly, also for the checks. So please select all of the beams, which are the primary beams, and deactivate these automatic buckling supports if they have not been deactivated by the software already. So this was about the buckling settings. And now I will show you the results. So let's again work with one slab. So like this. And I will go to internal forces. So maybe I will remove the columns to not interfere. Okay, so I will run for all of the beams, no filters. And here I will just run with this class composite design. Normal force, okay, let's show the normal force to prove you that practically we don't have any normal forces in these beams. Here we have some small numerical effects, but that can be expected in finite elements. And then here, let's show the moment diagrams. And what we see here is that is something that we would expect if we have our hybrid model without eccentricity and also tributary area base, etc. So let's maybe increase this. And what you see here, let's switch the values per member. You see here the size of the moments for the secondary beams, and for the primary beams, we get, let's say, this trapezoidal distribution of the moment diagrams. Okay, so now we have results and we can go to the composite service. So a few things that I would like to suggest when you use the composite analysis model. Here I will again select it with the columns just to give you an idea of one problem that you may experience with K-bracing. So interesting features when you're using the composite design module is, for example, the locking of results. So here there is a button which lets you lock finite element results. And when you lock them, you can practically do anything. You can delete columns, you can change cross sections, and you will still be able to use your analysis results. Then also here I've docked table results because I find it's also very useful when I'm using checks. And yeah, I think that's more or less it for now. I can go to the composite setup. So here, these options were available in the past. You can disable creep. You can disable, I think here, the fresh concrete in construction stage, the increased weight. But I will not talk about these options now. What is new is now this option design. So when you activate design, you have here some additional options. You can limit the depth of the beams. You can also choose the design approach. So here you can say, I want to minimize the beam size. I want to minimize the number of studs or something in between. So how this works, it's important to understand what is happening. So if I switch here to minimize beam size, it will try to achieve composite action 100%. If I set minimize number of studs, it will aim at 40% in most cases, and balanced 55. So in this case, if I change this value, I can also overwrite it completely, and I can select whichever value I want. This will also change the properties of the members. So what you see here, that the ribs, they're using the default value. The default value is from the composite setup, and it's 55%. So what this means is that when you change the number of studs during the optimization, based on this number of studs, we will get a degree of connection, which will also update. And this means that if you use fewer studs, you're going to get more deformation when you rerun the analysis. And if you use more studs, you're going to get less deformation. So again, going to the composite setup, I think I pressed cancel here. So let's use the design. Options related to the design is also now it lets you choose how many connectors per row you want to use. If you say 1, it means that it will always try to put 1 row of studs on the beams. If you say 2, it means that it will try to, if the beam passes with 1 row of studs. If not, it will switch to 2. So 2 is a maximum value. I think these things are also explained here in the remark field. And then there's also the possibility to design camber. So here is design camber, which is also new. And you can set a limit value maximum camber on the beams. Okay, so now I have these options and I go here, I have the composite beam design. These are the fire checks, which I'm not going to discuss today. They are the same as they were in 17.1. So here I have the properties of this check. I would like to run for all of the composite beams, no filter, and then use the class composite design that I have generated automatically. I would like to see the unity check per member, and that's it. So now when I run the checks, on one hand, it will run all of the construction stage and final stage checks, also ULS and SLS and detailing conditions, but it will also store the so-called design proposals, which are available from this button here. So I can go directly there. And I think I didn't show you the cross sections that I've used. So practically I have, for all of the primary beams, I have a single section. For all of the secondary beams, I have a single section. It's probably not the best solution, but I wanted to show you how you can split cross sections. So if you go directly in the optimization, it will switch all of your primary beams to this large section and the secondary beams also to this 450 sections. For the users who are not from the UK, this is an I section with a height 533 millimeters. So I can do this now, or I can use table results, which lets me easily split cross sections. So now I'm just going to practically show you the same thing that I see on screen, but now in table form. And I don't know how many of you are already using the table results, but it allows you to do many things. So for example, imagine I would select a beam from here and it directly selects it also in the 3D window. If I double click, what I see is the report of the calculation. So here I selected, there are 2 options, detailed and standard. For the standard, this is what I see for this beam. So let's go through this report and see what we have. So I have, this image is more or less dynamic. It gives you an idea of the sizes of the slab and the beam. The beam span, and then here you have the cross section, you have the material of the steel beam, you have the slab thickness and material, properties of the sheet, the shear connections, the shear connectors, which you can edit. I think I forgot to add that to explain this. In the libraries, you will have shear connectors, which you can edit. Also, here you have properties of the reinforcement in the slab. And then here you get an overview of the unity checks. So in construction stage, we have classification, shear buckling, shear bending moment, and LTB. In this case, it's not run because we have positive bending moments. There is an option in the composite setup, which you can, it defines whether you are welding the studs on the sheeting or you have holes in the sheeting and your studs are pre-welded. In case your studs are pre-welded and you have holes in your sheeting, you are then going to need to run LTB checks, which is, this is controlled via I think, let me see, welding of connectors through the steel sheeting or directly to the beam. In case you activate this option, you will also have an LTB check in construction stage. Then SLS in construction stage, just the deflections. Then we have classification, degree of shear connection, shear buckling, shear, reinforcement, bending moment, LTB. Again, it's not run, it's just listed in the tables. Longitudinal shear and crushing of the concrete flange. SLS in final stage, we have live load deflection, total load deflection. We have a very simplified vibration check, and we have minimum reinforcement for cracking. If I would now walk you through the detailed output, because I would like to more or less explain what we do on the level of the checks. So here this input part is identical, and then here you will see all the formulas that we use. Shear buckling for construction stage, shear, bending moment. Here we are checking whether the shear is more than 50%. If not, we don't need to reduce the bending moment resistance. So this is the bending check, the same as for steel structures. Then we have classification, and that's practically it. Here you see a deflection check. So we take the deflection from the finite element analysis, which takes into account the partial composite action. So now when I run the optimization, I will see all the unity checks update, but for the SLS checks, they will only update, of course, if I have camber. I see here already that this beam will require some camber. For the vibration checks, of course, this will not be updated before you run the calculation. So now ULS for final stage, and I will walk you through this, let's say briefly. So here we need to know how much the shear connectors carry. So in solid slab, we calculate certain resistance of the shear connectors, and then we reduce that, taking into account that the slab is not solid. So this is a secondary beam, transverse beam, and so here we use the KT coefficient. In case we have 2 rolls of studs, we will also see the K-mod coefficient. So here, effective width, I felt maybe this is more interesting to show on the 3D scene. And then minimum degree of shear connection, in this case 40%, and then it calculates the resistances of the concrete, of the steel, I think, of the steel member, and then it says, okay, for a value 55% of composite action, I need 9 studs on this beam, and then it recalculates the composite action. So 9 studs, in this case, it's trying to place 18 on the whole beam. So it's 9 studs from maximum to 0 moment. Keep in mind, this is before optimization. And then we see some standard checks. Vertical shear, bending moment. And here we can see the derivation of the bending moment in more detail. What we also have is the longitudinal shear. So here, shear which is transferred from the connectors. Here we see the resistance of the connectors to the concrete slab, whether we don't have too much shear in the slab. And then the next one is crushing of the concrete flange. Again, force coming from the shear connectors into the concrete slab, whether we don't have crushing. Now the SLS in final stage, we have live load deflection. And then we have total load deflection. And here you see it's proposing some value of camber, but of course, to get the accurate value, we should recalculate the project. And vibration check, here I want to put a little bit more attention that this is a very basic check and also relatively conservative. So what we are doing is we are using the simplified formula, taking deflections into account. So this is the deflection from the permanent load and 10% of the deflection of the live load. And based on that, we are calculating some frequency, right? And this frequency should be higher than 4 Hertz. Keep in mind that this is taking into account partial composite action. and also the hinges on the beams. We are looking into how to improve this check in version 18.1 so that it gives more accurate results. And because of that, this check is not taken into account in the optimization. And you can see it here, vibration check is greater than 1, and it cannot be changed by design. But I can show you how you can, what you should do in order to run this check correctly. So these are our checks. Also, I forgot to mention that there are two interesting options in composite setup. One of them is the possibility, if you have small negative moments, to check whether the steel beam alone can capture them. If you activate this, this can give you some benefits. I can demonstrate it afterwards. Then use concrete for shear resistance. If you have large shear, you can make use of the concrete in order to calculate the shear, because the default option, it only takes into account the steel beam. Okay, going back now to our checks, and wait, let's go back to the correct item here and to table results. So here we had this following situation. Now I will use a filter, so a cross-sectional filter, and I will select all of my secondary beams. So what I can do now in table results, I can select all of the beams that have more or less the same or approximately the same values of unity check, I think, without this one. So here what you see is I can switch to current selection, is now I can optimize these beams on their own, right? So I select here and I see that in this case it wasn't 450, but still it needs a UB 400, let's say 400 millimeters of a cross section. And here there is an option, modify unselected. So this means if I tick this option, it will change my whole model also on the other floors. If I deactivate it, it will now make me a new cross section. So what we see now is in the list of cross sections, I have a new cross section. I can also show it here. So this new cross section was generated for the selected beams. And so now, as I said, what you will see immediately is the effect on the unity checks for ULS. So if we run construction stage ULS checks and final stage ULS checks, we will see that now these beams are passing. Yeah. If we then, maybe we can, just to prove you that the SLS checks will not be updated, I run it again, and then you see that here it says vibration check. You can see these little arrows on the beams, which are telling you if there's any problem. Vibration check is not passing. If we select any of the beams and we would like to look at the unity checks, we will see everything is okay, except the vibration check, which will be improved when I recalculate the project. And here I see also the required number of studs. So going back to the other sections, I can show you that it can go quicker. Wait, sorry, not current selection, all. So let's say we are now running for all of the beams that we didn't optimize. I will select 3 of these beams. So these are the edge beams. I just go directly apply design proposals. And oh, sorry, I think here I need to switch to current and then directly go apply design proposals. I can switch these beams to 300 millimeters height. Okay. And these beams, I can, for example, I can select this beam. I say apply to this beam. It suggests 350. And this beam, 450. And then if you look here in the list, I have all of these new cross sections. Now I can do the same, again, switching to all. I can do the same for the primary beams. So I select these beams again. And then I can directly go apply design proposals. And again, I forgot to switch to current. So the only thing you need to do if you want to split cross sections is select switch to current. So here these will be a 450. And these beams 530. Okay. So if we now deactivate all filters, we can check what is the situation for example, final stage, ULS, and final stage SLS. Okay. Let's assume that because I see that I'm more or less running out of time, I will maybe skip some parts and I will go directly to some other interesting things that you can plot here. So if you want to verify the effective width that is used in the calculation of the checks, so I think, let me switch back to classes. So the effective width is available here. So in this way, you can verify, just to put you at, let's say, at ease, what effective width is used in the check. So you can see here that if you have an edge beam, your effective width is much less than in the case that you have internal beam. The same for these primary beams, you can verify. And also at the region of supports, the effective width is reduced. Another interesting result variable are these labels. So the labels, what they allow you to do, so here I will switch out the warnings. No, here, no, sorry, this one. I will switch the warnings off, and let's look from above. What we see here is this label is telling us what is the cross-section name. Then here, actually this is not the name, it's the designation of the cross-section, how many studs we need for this beam, and also if there's any required camber. In the case of primary beams, you will notice, for example, here we have more than one region. So we have, let's say, showing it like this. What this is telling you is that you need 7 studs in this region, 7 in this one, and 8 in this one. In the case of this beam, like maybe some of the internal ones, 16 studs in this, 10 here, and 16 here. So these are the labels. And another thing you can plot is the number of studs on the beam. And also you can see it in the table. So if you are doing some pre-design, you would like to know how many studs you're going to need for the structure, you can just copy this information to Excel, and there you can sum up the number of studs. This was related to the output. And then I will show you some other useful things you can do. For example, here you notice that by design, this beam is quite small. I think it was because of this bracing. I was going to actually run nonlinear analysis and show you that here, in fact, you are not going to get negative bending moment because of this bracing. This is a problem of linear analysis. Here you see your moment diagram. So now with this moment diagram, SCIA is trying to optimize and provide you composite action in this negative moment region, resulting in a huge number of studs on this beam. Here, I think is a good idea to use this option. You can define it per beam or on the level of the whole structure. I would do this on the level of the whole structure. Negative flexural strength can to be captured, negative moments to be captured by the steel section alone. And then I can switch to current. And then we will show, I like to use table results for this. I will show you that in this case, it will provide studs only for the positive moment, and it will give you a more meaningful design. So here I don't have the 50 something stats that were needed. So if I now run nonlinear results, what you will see is not only that there is no negative moment, but also here these moments will be much bigger. So in this kind of cases of a K-brace, it's advisable to use nonlinear combinations and run the composite design for these nonlinear combinations. Now, one other interesting thing you can do, we have primary and secondary beams, and we see that these secondary beams are below the, they are like higher than the primary beams. It doesn't make sense. What I would do here, I will simply grab this member. I would use the Format Painter or the Match Properties button, and I will select these two beams. And here it says certain properties are not transferred, but the ones that are important for me, the cross-section, are transferred. So that's the linear analysis situation. One interesting thing here, maybe I will first have a look at the questions, because I'm curious whether, yeah, I will have some time maybe to open to answer the questions. So in case of holes in the floor by a staircase, will composite design work properly? I think so, yes. So if you have a opening in this 2D slab, you model this opening, and then you model the beams around it. SCIA will take into account the opening for the determination of effective width. So in this case, your analysis model will capture bigger deformation because you have these openings in the floor. On that level, there are no problems. And also in the check is using practically the effective width, so it will not have problems with the openings. I also have some projects that I modeled and calculated with SCIA. If you are interested, maybe I can get in touch with you to show you some examples. So openings in the floor are not a problem. Then there is, what is it? Yes, what is the functionality in openings in beams? Yes, okay, so at the moment we have, let's say, limited support for web openings in the case of the SCIA module for composite. So what we have in version 18 is the possibility to include one web opening in the beams. So one web opening per beam. Yeah, and what we are currently working really hard on is for version 18 to have the possibility to have any combination of openings, let's say a rectangular next to a circular, next to an elongated opening within one beam, and then also if they are closely spaced to take the interaction between these openings into account. But this is version 18.1. Version 18 works as follows. So you for example, select one beam, this one, for example, and there in the properties of this composite beam data, you can include a web opening. And let's see here, I put, what should, for example, 200, then here 400, some eccentricity. So it guides you here. Value of opening, positive value is upwards. Let's put a negative one, and then distance from the start of the member to the opening edge, let's call it 300. Now, what is frustrating here is that the opening is not visualized and it's not taken into account in the analysis model. So if you would like to take it into account in the analysis model, you will have to define it twice. And this is version 18. So we have already improved it for version 18.1. But this is the situation at the moment. If you would like to have the opening at the same time in analysis and visualized and in the check, you will need to define it twice. So here again, I will have to put in, for example, how much was, this is the length was 400, here was 200, then there was eccentricity. So here is measured from the bottom. And then here, I think I need to, this is measuring from the middle of the opening. It's quite frustrating because the definition is different in the two different places. So here It's 3.2. No, sorry. Here it needs to be absolute. So 3.2 from the beginning of the beam, and this here. Okay. So here is the opening, and this same opening is defined on the member also for the composite check. And if I run now the check for this web opening, current, no filters, unity check. And so we see here now this is failing. Let's check the what is important here is the ultimate limit states, because ultimate limit states are influenced by the opening. So we had 0.94. Let's just have a look what we have as output. So here in the construction stage, we have a ULS of opening, and we have 4 checks, and we see the bending moment is at 94. And also final stage, I think it should no, I will have to double click. So in the case of final stage, okay, somehow exactly 1. And then let's have a look at the detailed output. So these are the checks we are doing for the final stage. I would like to look at the detailed output, and I will show you what checks we do. So these are all the normal checks without the opening. And then here you will have final stage. So what you see here are checks according to the SCI publication 355, P 355. And so you see we calculate the geometry of the top T and the bottom T. So the height, the area, the center of gravity, effect of high shear. There's no high shear because I put it more or less in the middle of the beam, so shear can be neglected on the moment resistance. Here it calculates the normal force resistance in the T's, and then this is the normal force resistance also in the concrete. It finds the neutral axis, and then it recalculates bending moment resistance. In this case, yeah, it's almost 1, not okay, because it's probably something here after the 1. Vertical shear, again, shear areas are calculated. And then here, the resistance of the top T, the bottom T, and also total resistance, taking into account the value of shear, then also the Virendale bending. Here we see unsuitable classification. If you see this, it means that we will artificially reduce the size of your T section. So there is the top T. In order to fit into class 2, we will crop some part of the web and make it into a class 2 cross section. And then the same bottom T resistance. And then these resistances. So here you see Virendale resistance due to the composite action. So it will take into account some contribution from the composite, and then the total resistance verified against the shear and also shear buckling of the steel section alone. Yes, so this is what we do for openings. And normally this should be included also in the optimization. What I've noticed is it doesn't work every time. So sometimes it's hard for the software to find a solution that will work in all cases. But now just to, maybe I will make the opening bigger to just prove you that it should work. And then I switch again. So now this opening is bigger, and you see the check is failing. So this is web openings. Another question. In what case should you use the advanced composite action? Advanced composite action is something that you can use if you would like to have a finite element analysis. You could use it in our footfall add-on. So we also released the footfall analysis add-on with our partner CADS. And there you can test the vibration of a floor according to the guidelines in the UK. And there you can use the advanced composite action or not. I think both options work correctly, but practically advanced composite action is there for our geek users that would like to have a very accurate finite element modeling of their beams. but also to use the rigid diaphragm. So I would not recommend, if you are just doing standard design, to use advanced composite action. Is it possible to have your model? Yeah, I think I can send it to you. Should I reduce the number of shear studs if the longitudinal stress is too high? Good question. What you can also do is you can add additional reinforcement via the composite beam data. Let's say that you are working with an edge beam, and here you can add additional reinforcement. You can practically change the reinforcement for that beam in particular. Or another thing you can do, actually, I see many people would like to use the composite beam design, but for the edge beam, they would simply want to design them as steel beams. What you can do is you can say it's without composite action. If you do this, then, and you run the check on it, what the composite check will do is it will show you an error and says members without composite action not supported. Please check according to Eurocode 3. And in this case, you can switch to the steel code check and check this beam with the steel code check. Can you show how to do the vibration? So there are two options with the vibration. I actually had planned it for today's session, so I will do it. So on one hand, you have the very simplified vibration check, which is just looking at your frequency. This you can do in SCIA Engineer. On the other hand, you have the vibration analysis, the footfall analysis, which is done via our footfall module. And if there are let's say participants who would like to see this module, we can organize another webinar about this. So, but in short, what this add-on does is practically you need to grab this floor. You need to take also the columns, so these two columns with the floor, everything the way you've modeled it. Reduce the size of these columns, support them, simply support it here and here, and run model analysis. And then you practically just export to the add-on, and there it can check footfall in quite advanced ways. But I'm not going to show this option today. We can organize a separate webinar for this. Now, the other option is if you want to just check the frequency, what I would advise you to do, because this vibration check is very often failing, I would advise you for the normal check to ignore it. And then after you're finished with the design, if you had any vibration issues, just delete the hinges. And the next thing is to select all of the beams. And instead of this default action of 55%, actually, or partial action, here I switched it to a non-composite beam. So I select these beams and then I switch to full composite action, because you are allowed to do that. Normally when you do vibration analysis, you can actually even increase the modulus of concrete to the dynamic modulus. But I will just recalculate now. And I will show you that in this case, the vibration checks will actually look completely different, because now you have much more stiffness, so your deformations will be smaller. And so I would advise you to run the design and then have all of your studs and cross sections and camber. And if you have any vibration problems, then save into a new name. And then do what I told you. So delete all the hinges and switch to full composite action. Now, if you go to the composite and you're going to rerun the checks, you are going to see very different results for these beams. And the reason is you will have everywhere negative moments. But for the vibration check, I find that this is more logical, because in the vibration scenario, you have much smaller deformations. So you will not have a real partial composite action. You're not going to realize these deformations between the slab and the beams. And here, an easy way to check whether you have a vibration check failing, I will show you here all of the tricks, tips and tricks. There is a specific warning for vibration, and that's the W31. And here I see it on this beam. So now if I look at the report for this, you will see all of the checks are failing, but the reason is that now I have this bending moment diagram. So this is not the bending moment diagram that I would like to use in ULS checks. But if I look at the deflection, so in the vibration, I see this beam is failing. So it is this beam. So in this case, with these boundary conditions, I know 100% that I'm going to get serious vibration issues with these beams. But with the other beams, if I grab even this one, you will see that vibration is not really a problem. So this is my opinion on vibration. Okay, so I think these were, for the ones who want to stick around, I will just show you my presentation, which is saying everything that I showed today, but I will just go through some important things to remember. So here we started with a normal steel structure. We added 2D members, composite deck, rigid diaphragm. We defined some thickness, some material, right? Then as soon as we modeled this, it told us that there will be partial self-weight load cases for the fresh concrete. And then we saw these load cases being generated. Then the tributary areas, two properties control the tributary areas. So it's the local coordinate system angle. So initially we got this. If we change the sheeting orientation, the load-bearing direction changes, and we got this. Then we also changed the tolerance. We obtained these tributary areas. Then we connected the 1D members as ribs. And then we had the effective width automatically calculated. We can override this automatic effective width with a manual value, and that will be taken into account in the analysis and in the checks. Also, system lengths, I advised you to check what's happening with your primary beams. In some cases here you may get a support, so the span will be very small. If you want correct calculated effective width, please untick these supports. Then I showed you the difference between the analysis model and the structural model. Here is the point is to use standard composite action and to use the so-called structural model where you can show the structure in a nice way. I showed you linear analysis results with the assumption of rigid diaphragm and tributary areas, that everything works as simple beams, or if you remove the hinges, of course, here you will have negative bending moments. You can also do that, but the normal force is eliminated by using the standard composite action option. About the loads, here was the load of the sheeting, load of the fresh concrete, and the dry concrete. Also, taking into account stages, this property is very important. Construction stage, final stage long-term, final stage short-term. Automatic combinations. So this is also in the framework of automatic construction stages, that the automatic combinations are generated per stage and per limit state. Eurocode 4 checks. I showed you how to use table results to get result per beam easily. And also here I showed you what checks we are doing for ULS, for SLS, construction stage, and final stage. I forgot to mention the detailing checks. So here, for example, if you want to see that what is interesting, that the sheeting rib is not above the height of the slab. That's important. Or, for example, that you have enough spacing. For example, here, minimum distance from the stud to the edge of the flange of the steel beam. So if your beam is too narrow, then maybe you can't actually put the stud there, right? These things are taken into account in optimization. So SCIA will automatically switch to a beam that has a wider flange in order to be able to place the stud. Here I showed you the detailed output with all of the formulas. And for the design, I showed you the options that you can minimize beam size or minimize the number of studs, or you can define composite action that you would like to aim at, and this will be taken into account. And here also the option to design camber. You can also deactivate it and say, I do not want to use camber in my beam, or you would input it manually. Here I showed you result locking. It's really useful because otherwise every time you change a cross section, your results will be deleted. And table results with all of the result variables. So you have unity check, the labels. Here C equals 10 millimeters means the camber is 10 millimeters. And here this is total stats. I hope it's a little bit clear. If you read maybe the help, you will know what TS means, but it's total stats. And also using the filter is useful when you're doing optimization. Output, we have again the brief output. So the brief is available in the 3D scene. You see all the values on the screen, table results, preview, and engineering report. Here you have the labels, so the name of the cross section, the studs, and the camber. Here, this is the possibility to show effective width. I've used the rainbow color option in this image. So this is effective width, smaller for the edge beams than for the internal beams. And here you see the stud layout. So here it's offering you two layouts, one uniform and one segmented. It's maybe not the best choice because in this case, they're almost the same number, but in some cases you will see that in this area you will get much fewer studs. And here in the web openings checks, I've added some examples of what is supported. And this is everything. So for the ones who wanted to have the model, I will get your data, your email address, and I will contact you afterwards with the presentation. The handouts will be sent to everybody after the webinar, and also a survey where I would put the question, would you like to see the footfall module, for example, and then we can organize another presentation for the footfall. Okay, I see some people responded they also want the model. Okay, I will send it to you. And I think that's everything which I wanted to say today. So you can ask your last questions and I will respond to them, and then we can close the webinar. Okay. Thank you very much for attending this this session, and don't hesitate to contact me. I think my email address was in the invitation, and if you have any questions after. Thank you very much, and this webinar will be available online on YouTube in a few days. Thank you.